Okay, let's start. So this is just a simple electrical circuit, you can say. So with the DC source, so the switch is basically closed at time t equal to 0. So you just have to express the output voltage. Okay, so I mean, it's just a simple electrical circuit. Maybe you have solved this one in circuit 1. So you can say, before you close the switch, this output voltage here should be 0, right? But once you close it, then this one is shorted, right? So this means that the voltage acquisition should be the source voltage. So mathematically, you can write this way, like, from minus infinity to until it is 0, it should be 0. But once it is 0 plus, once you close this one, this should be just the source voltage. So you can write this one up in this way, right? So this is the expression of the output voltage. So through these two limits, you can make it specific. Okay. So and you can draw this way, right? So one thing you can see, there is no value of this signal at t equal to 0. Okay. So it is equal to t plus or t minus. Yes, what's the problem? Yeah. Does anyone ask any question? Okay. So so here the point is that, given this kind of expressions and the signal responses, so is that possible to represent this complex form of as, the output or the system response in terms of some with some elementary functions, more specifically if it is unit step, because you can see this it just simply nothing but an unit step response. So that's actually the point here. And so unit step function, the way we define this one is basically these values for only t is greater than zeros. Okay? And for any value t is less than 0 is always 0, but at t equal to 0, the function values is 0, and actually undefined. It's not actually 0, rather you can say it's undefined. In fact, it actually represents, at t equal to 0, there is a transition from 0 state to state 1. Okay? So this is how we represent it. Maybe in some books you may find this one, they also use this equal or less than, equal or greater than zeros. So in such a case, there should be some impulse response here at this point. So anyway, this is the typical expression. At equal to 0, the signal value is not defined. Never say that it's 0 or it's just simply undefined. So for less than, it's always 0, and for greater than, it's always 1. So now using this, unit response, it is possible to express or to define the response of any practical system. That's also possible. For example, if you do not start it from 0, but maybe at some point t naught, which is greater than 0, so you can also represent the system response just by t minus t naught, because it's just a delayed by t naught. So this is also unit step response, but delayed by t naught. Okay? So you can say 0 when it's less than t naught, but greater than t naught is always 1. Okay, and if it is if it is for t minus 1, so it means you start from here, so it's a little bit advanced, right? So there should be t plus t naught. Minus becomes plus, because it started before its normal values in time t equal to 0. So yeah, that's actually the next expression. So now you can let's try this unit step response to apply here in this circuit. Is it possible to just define the response of this circuit in terms of this unit step or the elementary function, as I said? So here you can see, instead of zeros, the switch is closed basically t equal to capital of T. Okay, so everything else is the same, right? So this means that any value greater less than T, the system response is 0, and greater than T, the system response is basically the output. I mean, the output is basically the input function. So you can easily write this. So the response should be like this, yeah? And you can easily you can see this B as different magnitude and multiplied by unit step response. So the signal, I mean, this output has only values because it's a unit step response. Only values where T is greater than T, capital of T. Other than that, it just only is zero. So you can see the system now becomes so very simplified expression. So, you don't need two entry two intervals and represent them separately because this function u is just say no. So it's for mathematical simplicity. You can say these elementary functions. I think we already mentioned this in many cases. Very complex expressions. It is very difficult to analyze. But once we have this kind of elementary functions, we presented that expression, so it's very easy. And you can say that, okay, yeah, even by observation, it's also possible to draw a conclusion on the response of the signal. So other than this, you may have many kinds of signal response. We can try this one also. For example, what if it is the case for, I mean, other than this, uh, for example, how do you define this one? Very simple. You just try this one. What if we try this one? What should be the expression of this? This one is what? A minus a u naught minus t plus t, right? So maybe you can write this one here. Okay, just a minute. So minus, what if it is, okay, let's say amplitude is given, and the unit step function is defined, for example, minus t minus t. So now if I'm asking you to draw this output response, although this signal, yeah, the output and input is all a signal to the signal response that is represented in terms of this unit step response. So we can do this. So you just have to start from scratch. So first of all, you have to find this one. Okay, you can see this. Okay, just start from this one. So u minus t. So this means that here we have basically in the time reverse operation, right? So if it starts from here, because due to this minus t, it's basically start. I mean, the signal has response here, right? Just response here. And it's negative values is this. I mean, just for this one, only consider up to this part. But and then what do you have? Let's say minus t. Minus t difference is a delayed form, right? Normally, so if the nominal response is from, it should start from zeros, but, but now it is a delay. When this signal is delay, this means it should start from here, right? Because it is delayed by some. It's a reverse response. So it means here is the t. Okay? So now it's basically it should start from here, right? And then okay. So and this is the values of a when if this one is positive. Now you're done. But what if this one is negative? So you just have to flip this one down. Okay, so it basically starts from here, right? So it's a minus one. Okay. So this way you can also show this and the different results. Now your response is basically this one. When you consider minus of a, the rest is as it is. So let's check whether it is okay or not. So when you see, so it's a minus of a. So this is the response basically we asked for. So hopefully you should be able to draw this kind of thing. So let's start with the normal procedure. So this one is for minus t, right? So what if this one is a plus t? This means that you are actually working in this side, and everything else is the same. For example, t minus 10. So it should start from here. Okay. So for plus. So if it is this one is if it is minus this amplitude, then it should start from okay. For example, it should start from here. So this is the response over here. But make sure that we also represent this other part. So this is the response of this. So you can check this one. I mean, the response of this. Okay, my uh, positive values of t. Okay, t plus t minus ac. What is that? T plus t. See t. Start from positive values of minus a. Wait. Oh, it's negative, right? Okay, that's okay. This one. So it's okay. The same thing. So if it, I mean this, whether you will use this quadrant or this quadrant, that's actually, I mean, in fact, not this one. This whole quadrant or this whole quadrant is defined by this positive and negative sign. If it is a negative sign, you will work on this side. Okay? On the bottom layer, you can see if you take this one as a reference, bottom half, or if it is a positive, then it's the upper portion. Okay? So any question here? So you're supposed to, answer this kind of. I mean, maybe let's say you're given with some function. Now you're asked to draw, or maybe you are given with a function. Okay, the response of this function, and you're asked to find this mathematical expression. So it should, I mean, both of it, you may have this kind of questions. Okay, so that's what it is. This is just an example like how we can apply or use this unit function just to represent the sequence. So this is another okay. Uh, well, any signal response event can be represented, as I said, with a combination of unit step response. Okay? For example, you're given with this. Now, if you're asked to represent this one, okay, what is it? Represent this one in terms of unit step function. So let's try this one. So here we have okay. So for example, let's say for example you're given with this function. So it's a plus one. This is also plus one in time and magnitude. What will be define this? Okay, magnitude could be anything. For example, let's use this one as well. B of t. So now you have to represent this one just for example using a unit step function. Unit step function. So, so what do you have to do? So this means that first you can see it start from the origin, t equal to 0, right? So it means that the component signals, even if it is a unit step function, it should also start from the origin. And because it is also positive quantity, so there should be positive quantity here. Okay, but it's it's lasts until t equal to infinite, but it lasts only up to t equal to 1. So we need another function here. Okay. So which basically lasts up to what? Uh, okay, we just need the response and something here. This is also up to infinite. This is 1. Hmm? 1. This is minus 1. So here you can see up to this 1, so you have only this much because this one is 0. But after t equal to 1, so these values and these values are cancelled. It's up to infinite. Right? So what you can write then? An initial response. Okay. What you can write? So it's a summation of these two signals. So u t, right? Because it starts from 0. Okay. And the magnitude is just 1, so it is as it is. Because the unit step response magnitude is 1. And then it's a plus sign. Is it plus or minus? It's plus sign because if you plus it, then 1 and minus cancel each other. So you have t minus 1. So this should be the response of this p of t. Okay? So this is just a, you can see, so this is it. So here you understand, I mean, any signal, so long as it can satisfy the basic properties of initial function, you can represent that function with an elementary signal. So now here is the easiest option is that you don't need to work with any signal or system response one by one. Here you have only one thing in common, that is actually in step response. So just if you know this response characteristics, everything else is basically easy for you. So it just makes you the independent of any system characteristics. Otherwise, you have to work with each of the system response or the signal response separately. So this is just a way to, I mean, this mathematical analysis make it easier, yeah, and simpler. So it's just an example. For example, okay, what if you are given with it's a square signal, right? A periodic signal here, as you can see. So this even can be represented. So you don't need to analyze this signal, for example, with a Fourier transform or Fourier series, how should have the response. I mean, if you know the Fourier series of response of this unit step function, that's fine. You just have to change some parameters. Like this one, you can represent ut minus t, right? Okay, so you have ut from here and ut minus t from here. So this two is cancelled, so you have this b1. And for b2, so you start from t and end it, okay, what? Twice t. So ut minus t, then minus ut minus twice t. Okay, and magnitude you can see it's a negative, so there should be negative values. And so is the case for R also. So b3, so twice t, thrice t. And if it's b4, there's a negative value, but it's a 3t and 4t. So this one actually just represents only that portion of this signal. And this way you can continue. Okay, just sum all this. This will give you the response of this signal in terms of instant function. So that's actually the added advantage. Okay, uh, I think it's the same thing. You can do it by yourself. Okay. I think, as I said, you just have to sum all this. So you'll, and it will be continued. Why? Because uh, the value of t is basically tends to infinite. So it will be continued. Okay. Now, what if you are given with the bounded signal that's is bounded in time by minus t by t to t plus t over 2. Okay? So that can be represented. How we can do it? Okay, how do you represent this one? Hmm? Here you can see what, okay, is the signal actually is, if it is a unit step function, right? We have to represent the unit step. You can see express this symmetry because it's around this y-axis is symmetric, so it's real value signal. The symmetry rectangular parts, okay, of this figure as a sum of unit step function. So you have to represent as a sum. So one start in advance, right? So it's actually what? U of what it should be? What's the value of this? You have t minus t by 2. So you have t plus 2. T over, I mean, like, okay, that should be like u of t minus t by 2. Okay. So in fact, it will be actually u of t plus t over 2. And the second part where it's ended. Because one signal already started from here, right? The other will be started from here. So only this part will be left. So that's actually u of t minus t over 2. I'll just do this one here. So this should be minus u of t minus t by 2. So this is the response of the signal. Okay. So it's the same thing. So here I have shown this one is one. So you may have a different, the difference here will be, and the signal will not be the same, right? So you just have to understand the signal properties and how you can express it with the unit step function. Okay. Yeah, there are a few others as well. Let's try with this one. So you can see when it's just rising from minus t by 2 up to 1, right? And falling at the same rate at plus t by 2, but t over 2. So you just have to express this. It's also symmetrical, but it's a triangular. And it's also represented by sum of instead of response. So how do you, I mean, how do you find this kind of signals? You know, I mean, because here the function is not defined. Is it increasing again decreasing? So you have to first define the function. Okay, when you have this kind of stuff, here you can see easily understandable. This function is defined at values plus a. So we don't need to think of anything. Right, and any example we have given, it's all is the fixed values, like you can see. But here it's not. This is not actually fixed because it varies as the time changes. The values also changes. No matter if it is linear, non-linear, whatever, but it changes, right? So it means in both cases you have to like identify. I mean, for example, when you are able to identify this signal response, and also you have this one, right? So we have to identify this signal responses. So these are the two cases. Huh? So let's try this one if it is possible or not. But if we take this one, okay. Let's see this one first. When you have this kind of response, what will happen? Let's show the signal first. Let's see. So we have the signal. We, what is it? It's given as it's given as the signal. This is the signal. Okay, maybe it's not 100%. Okay, and this one is t over 2 in time. The value of the magnitude of the signal is 1. And this is the signal video. Okay, so you are given with this. Okay, so now you have to express this one as the sum of unit step response. The first I mean, you have to represent these two signals. I mean, two parts of the signals. For this part, so what's how do you define the these points? Here you can see we have the values of y-axis is 0, right? And x-axis minus 2 over 2. And how about this one? Here x-axis is 0, right? Value of x-axis here is 0, but y-axis is 1. Okay? Now we need this one. And we have all these values. So what it should be? Here the y-axis is 0, but x-axis is plus t over 2 and then 0. Okay? So this is what you have to do first. To define all those possible uh, points that can help you to define that functions for a particular segment. Now, for this segment, let's say this one is segment A. It is segment A. So how do you find the values of A? So you can find the slope, right? So finding the angle. So how do you find the slope? Remember? Or maybe we forget it. Y2 minus y1 x2. If it is, because it's linear equation, you can see this one. It's just a linear equation. It's a line, equation of a line. So here is an x2 minus so. So y2 is given 1 minus and the, well this one is what? Oh okay, I just made a mistake, right? So this should be 0 and this should be x because this one is x, this one is y. At this point the y should okay, let me see. Oh, estimate. So this should be actually x is actually minus t over 2 and y is basically 0. That's the same. And here x0, y2. So here y2 minus y1. This means minus t over 2. Similarly, x2 minus x1, x2 is 0 minus x1 is minus t by 2. Okay, so you can find these values. What is it? This one is 2 plus t, okay, 2 plus t, right? And here we have plus, right? Plus t over 2, right? Oh, it seems to be like that. Okay. Where is the question I can see? Okay, is it okay? Is it seems to be okay? Let's try this one again. For this shouldn't be any problem. So this is your slope, and the slope, this it is an equation of a straight line. Y equal to mx plus c. So the value of m we have already t plus t over t by 2. Okay, multiplied by x. X is basically okay, x plus c and y. Here y is basically b and x is basically t, right? So you can consider any value at this over this signal. So let's consider this point because this is the expression of this. So you can consider any point. Maybe this one, or maybe any point here. And since we have already defined 2 points, well, maybe you can use either of these two. So y is equal to, so this one multiplied by x1 equal to what? This 0 plus c. So here you can see you have found the values of c equal to 1. So now you should be able to write the equation for this part because we didn't know the values of this c. So at any point, as I said, uh, what is it? Um, y m c equal to 0. This means y equal to mx, right? So y means what? Y equal to bm into x values. This means b t for this part y equal to mx. M is this one, right? 2 plus t over t by 2 and x actually is basically t. Okay, so let's see this one. Actually, let's calculate this. It seems like it's t 2. Did you make any mistake? Y2 minus 1, next one is 1. Minus zeros, 0, 1. Yeah, it's everything same. Y2 minus y1. Come on, y2 minus 1. You see, no one is telling me anything. This is y2, 1. And y1 is 0, right? This should be 0. Uh, and x2 is 0. And x1 is 0. Yeah, that's okay now. So you have 1 there, right? So this should be actually t over 2. Okay. So this is actually t over 2. Hmm, t over 2. But it's okay. There shouldn't be any changes here. So this will be basically the value of this will be what the value it should be. So y equal to, because c equal to 1, right? What you can write then? We have this slope t over 2, and this x is basically t, and c equal to 1. So this is the expression for this part. Yeah, I think it should be okay now. Yeah. So you can say t over 2, t plus 1. Did you get the point how to find this, the expression of a straight line? Any confusion here? Hello? Are you there, anyone? Hello?
No
Yes,
problem.
sir. We are there.
Are you attending the class or sleeping? Huh? Are you listening?
Yes, sir. We are.
Okay,
Yes,
do
sir. We
you,
are listening.
so do you understand how to find the expression of a straight line?
Yes, sir. Yes, sir.
More or
Okay.
less, yes.
So long as it is not steady over time, then that is how we have to find it. So your first task is to identify all these points, an end point of this straight line, where you need to express. Sorry. So okay. So once you define these points, then you know this expression how to find the slope of this straight line. That is actually y2 minus y1, x2 minus x1, and that's you can easily find. Once you find it, this is basically you need, right? But since it is mx plus c, we don't know the values of the. So use this expression mx plus c, and then take any point, because the whole point you can take anywhere any point, and you will see the result will always be the same, because this is the expression of this straight line. Okay. So if you now put the values of m and then t and y, so you will get the values of c. So you are done. mx plus c. So that's how you can find it. So you can easily, so you can now check by yourself, and you will see if it is for this downward, this is upward to downward, then you will see it's just plus 2 over t, here will be minus 2 over t into t. Okay, this is only the difference. You can check it by yourself, just following the same. So now we have the expression from minus t by 2 to 0 and 0 to plus t by 2. So we already have this expression. So the whole signal within this time boundary, okay, we have already defined because it started and at this point and increase up to this point and then falls to this point. Okay, so and you can easily define now the, okay, here you have unit step function. If a unit step function, just try to understand, it doesn't have any magnitude. It's basically one unity magnitude. Any magnitude means, I mean, other than one, just unity means one. So anything you multiply by one is always, I mean, that value or that function, whatever you say. So whatever you multiply by unit step function is basically, I mean, it basically that function. So you can start from u t minus t by 2, which means u t plus 2 by 2 up to ut, and that should be multiplied by this because within this range, okay, because one start from here and the other start from here, so you have only this part, and within this range you can see the way this t changes, it changes, the value of this one changes. Similarly, from 0, I mean, ut minus ut minus t over 2, and you have the function. Okay, so and then sum these two, so you'll have the actual expression. So this is it. With the point, so the resultant expression is the same, and that is how we can express on any given function in terms of unit step function. Just make sure that if the function value is not constant, rather it changes, maybe linearly, non-linear, or whatever, you just have to express that function uh, or for that, for the portion of that of the function, using some non-mathematical tools. Like here we use the straight line tools because it's a linear function of t. Okay, so this is where you have to end your solution. Hopefully, you should be able to. So you will have this. In fact, as I said, only maybe the changes in the signals. Uh, the procedure is the same. And now, how about this one? What do you think? Express this way from. Can you try this one? Express this way from as a sum of unit step function. So here you can see, I mean, just see the response of the signal. So this one is actually inclined. So it's not fixed. It's a linearly vary from 0 to 1. Uh, in values is from 1 to up to 3. I mean, within time interval of 1. And then you can see the signal remains constant from 1 to 2 time interval, 2 units of time interval. And then there is a sudden fall. So sudden discontinuity in the signal to 1 at point 2. Okay, so there's nothing to represent because it's just a simple impulse response. So it's not even an impulse, we cannot say it, but it's just a sudden, within a short period of time. Uh, yeah, you can express it in a sense that this is definitely impulse response, but this is, we normally say it is a sudden discontinuity. So we'll not, how do you say, well, I mean, represent this part basically. In fact, as you can see, this unit step function basically does not represent at the boundary because the point where it started or ended. In fact, ended is infinite, but we mainly look at the starting point. Okay, so the starting point is basically it does not include the starting point. Okay, which at the starting point we consider that there may be transition, okay, from 0 to 1, but we don't want to see how it actually happens. So it means at a particular point you don't need to think of, I mean, whether the unit step response can you know can represent the function or not. Because even if you start from ut minus 2, in fact it is actually ut minus 2 greater than, when greater than ut minus 2. I mean, the value of this t should be t minus 2 greater than, not, it doesn't include that point. So it's okay. I mean, you can use up to, this unit step function, no problem. And then we can say we have one more variations, right? And this is linear variation by one unit, both in magnitude and time. So there are two variations. So it means you have to first find the response of this and the response of this. Okay. So can anyone okay try? Okay, I'm just giving you 5 minutes. Huh? Just try this one. Just find the values of this, the expression of this. Okay, and tell me the answer. Do you understand? Okay, just try it. Try it. Huh? Just within 5 minutes, just try it. And once you finish, you just simply raise your hands. Only for this part. Huh? I'm not asking for anything else. Only for this part. It should be always. Yeah, just only this part. Huh? Just try this. You mean the result is okay? Just a moment. So as you said, the result is b equal to twice of t plus 1. How about others? Is the same result? Did you get the same result? Twice t plus 1? Hello? I can't hear anyone.
Yes, sir.
It's the same result. I mean, like this twice t plus 1?
Yes, sir. For the range t greater than 0 and t less than 1.
Yeah. So you're absolutely right. You said twice t plus 1. So you can see. So it's been said you have understood, okay, how to find this, find the expression of a straight line in some portion of a signal. And similarly, you can also try this one. Then you'll see the value of this one is actually the, I mean, the tangent. I mean, this value or slope is basically minus 1 with c equal to 3. So it's a minus t plus 3. So we have the values of this, and this. So these are the three segments of the signal over the range of t from 0 to 3. So we can now represent from ut minus 1 multiplied by this, and then ut minus 1 minus ut minus 2, where this value is fixed, just a fixed value constant. And then from ut minus 2 minus ut minus 3, multiplied by this here. Okay, so you can see, so the first values, second, and the third. So this is your answer. So if you just simply leave your answer here, it's okay. You don't need to manipulate everything. If you do not have time, just leave it as here. It's okay. But if you do further manipulation, then you can even simplify it. But I don't think that will basically give you new information. It just simply hard working, nothing else. So just leave it as here. That's it. So I hope if you have this kind of problems, you should be able to answer. Right now, if it is a ramp function, sorry. So if it is a ramp function, as you know, the expression of ramp function is okay, for any value that less than zero is zero, and equal. It's equal and greater than. So it includes the point t equal to zero. So the value of the signal is the value of the independent variables. So that's actually the properties of the ramp function. Okay. So this is actually the ramp function properties. If it is unit ramp, it means I mean, I'm not sure. Unit ramp, yeah, it should be, that's okay. If it should be anything, it's the same. T equal to 1, it should be 1. Yeah, that's okay. So this ramp function we can represent, right? This unit ramp, or the other way you can say. So from 0 and onward it has values. This means that, um, well, just a minute. It's maybe the other way. I think we have already mentioned this one before. So a ramp function can be represented in terms of unit step function. How? Just by integrating that unit step function. Okay. So if you go up to t equal to 1, the value of t could be anything. So it just starts from minus infinity to up to this. Right? So you can represent, okay, if it is a unit step function, okay. So and this one is a ramp function. So any value, okay. I mean, it just because for unit step function, this value is basically 0. Mm. So you have basically this part left. Mm. So and this is basically an unit step function. It means the magnitude is 1. So this means whatever the value of t is basically the value of the function. So in short, it is just the integration of the unit step function, or the other we can define the differentiation of this function. So if we just differentiate a straight line, we basically see if static value of the straight line, but this one is actually uh, in a straight line with almost 45 degree, or with the slope of 1, because these two values are the same, so slope is 1. But here the slope is 0, right? So the major findings here is that, I mean, you can simply swap these two function response. One just by integrating a unit step function, you will get the ramp function, or if you just differentiate the ramp function, you'll get the its corresponding unit step response. In some cases, you may have to, swap these two functions, so just for your understanding. So this is another example, like if it is an RLC circuit. Okay? So here you can see the network has a constant current source, I of s, and its closes at t equal to 0. Okay, now this is the voltage across this capacitor. You have to find actually the voltage across this capacitor. And the switch is closed at t equal to 0. So find these values as a function of these unit step response. So, mm, okay. So this one is the, as you can see, this one is a fixed values, right? So fixed, it's a DC current that is given by it's a constant, as I say, to any value that is I of s. So if you just start from minus infinity to up to t, if it is a capacitor, it's what you say is the initial values. The t of this could be anything. Right? Here it's like it's a t equal to zero. The general expression for a voltage across a capacitor is this. So 1 over c division of I dt. Right? So at t, okay, since the switch closes at t equal to zero, it means we express this IC. This IC is basically the current flowing through this. Huh? So we can represent IC is equal to IS because this is it's a fixed values, right? And it's the unit step response. Because unit step response start from t equal to zero. And we have also closed the switch at t equal to zero. And then it remains constant as it is. So I mean, constant value is given by this IS. So you can easily represent this current in terms of this IS, right? Just this one multiplied by u u of t. So in fact, we need to find these values, right? This IS, IC. But as you can see, for t is less than zero, we didn't define anything. This means we assume that its initial condition is zero. This means before we close this series, okay, we assume that the voltage across this capacitor is zero. So the initial condition is zero. So other way we can see minus infinity to t. So this one we can represent two ways: minus infinity to zero and zero to t. So this t now it says is zero, okay? But it could be any value. It could be, let's say, t equal to t. So it means 0 to t. It's a general expression. This one. So what we have here, okay. So this one is 0, as I said. There is no voltage across this capacitor. But this one, is for making my life very difficult. Okay, let's get back to this. So now put these values of IC here. You can see IS you can easily take it out of this integral. This is a fixed quantities. This one is a function of this because it's not, this unit step function is not fixed. I mean, the value is fixed, but it always has some values for any values of t. So, so we use a dummy variable term because t is we already make it specific. So once this one is zero, so this can be replaced by is over c t. Okay. You and this unit step function. That's it. So basically, in fact, you will have this kind of response where the slope is defined by this ISMC and the unit step response is this. So it's from here, any value of t greater than 0, you have the signal response. That's right. This, in fact, if you can see this response, this is actually the ramp function. In fact, the one way to figure it out whether the function response is ramp, just make sure that there is a presence of independent variables with order 1, not more than that. That I mean, just to make sure that this is a ramp function. Hmm. But if it is a unit step function, it's a zero order. So t to the power 0 means it's a 1. Okay. So for unit step function, the order is 0. if design function is order is 1. So the presence of any t or any independent variable with order 1 is the response of this function or the signal is RAM function. So this is it. You can see the capacitor is, I mean, if you just try to understand this concept, this means once you close the switch, that's what you know. If you also remember these things. Once you start closing this, it start increasing, and then it's again started decreasing. It's a discharging phase. Again started increasing. You remember this? Maybe you have seen this one. So this one is a charging phase. This is a discharging phase. Or a capacitor. That is the voltage. And this is actually the case. But here we didn't consider any discharging phase because once you close the switch, we didn't open it. Hmm. So if we open it and if we have another circuit to make a complete loop, then it can start discharging. But we just need to consider discharging phase. Okay, so that's how you can represent the voltage of a electric capacitor. So this is just RL circuit. Huh? The one before was RC. It's RL. So here you can see the switch. I think it's the same thing, right? So only we change the parameter in this. C is now replaced by this L, right? So what should be the response of this RL circuit? So this one is also closed at t equal to 0 and IL t equal to 0. IL means t equal to 0 means its initial values, you see, for t less than 0, its initial values is 0. And now you have to express this current in terms of this unit step response. So they have already made it clear. The initial condition of this inductor is 0. So you can assume it as a 0 condition. Well, that's okay. Let's try to solve it just following the previous problem. As you know, the generic expression of voltage across an inductor is L into di by dt. Right? So since the switch closed at t equal to 0, okay, switch closed at t equal to 0. We understand switch closed at t equal to 0. So it just started. So it's we can use a unit step response. Once the switch is closed, so the current started flowing because it's a closed circuit, right? So and the value of this IL changes the way the circuit changes. Okay, so and because unit step function doesn't have any effect on the magnitude because it's only one. It's either you can say whatever you're multiplying with this, let's say is so the resultant function will show the response of this x, not this unit step. But it can help you define the boundary in time. Okay? So, okay. So INT we can represent. Okay, so at t equal to 0, even just looking at this one, you can understand. It's a unit step function that starts at t equal to 0 with a magnitude is. That's it. Yeah, and it should remain in this below because once it's a DC bulb, DC current, and this is an inductor. So it means that the impact of this F is basically because it's zero, right? It's zero, and since it is zero, so we can say that the values of the x of L is actually twice by f of L. Right? So this one is zero. This means this is also zero. So the impedance here is basically zero. So we have only the resistance there. The resistance does not change over time because it's not a function of time. Even though, yeah, with temperature it changes, but this one, I mean, we do not consider. So it means that the current that is flowing through this should be fixed. So we can represent this IL in terms of this unit step function. So now put these values of I of L here. So we'll say, okay, L is is a derivative of ut. Derivative of ut. Can anyone tell the derivative of ut is what? Hmm? If you take the derivative of ut, huh? Hello, what? What's the value? Yeah, it's a derivative of ut, right? It means you are, I mean, the voltage across this inductor is expressed as the derivative of this unit step function. What do you what do you understand from here? Do you understand from here? Yeah. So what does it mean? Unit step function, the values is fixed. So if you take the derivative of any fixed values, I mean the result? So BL should be zero. BL is zero. So what have we have done so far? Is it correct? Why? Yeah, I understand. I mean here is zero. But do you think the result is correct? I mean theoretically, what do you think? This is through some mathematical. Why? Overall result should have been zero. So you also got zero. What's the problem? I don't understand. Do you get the point? Here, after calculation, you found that this is the expression. Now, if you put the values of this unit step, you see that BL equal to zero. My question is, that do you think the result is, or your answer is correct? You're just making me confused. Anyone else? Hello. Do I have only one student today? I think I can see there's so many. Do you understand? Here I can see 32 students. Where are they? And they just seem to logged in and gone.
Um, sir.
No, sir.
No, sir.
No, sir. We are here.
No sir, no sir.
Yes.
So what I'm asking, then tell me something. What do you think? Is this result correct or not?
It,
You have already given the circuit, and following the circuit, I mean, through your calculation, you have found, okay, this is the expression for BL, which is basically the function of the derivative of unit step response. Yeah. So do you think the result, this calculation or the result of, for BL is correct or not?
Mm, mm, it's a highest height.
Is it very difficult? I don't know. You have to answer this one. It's not confusing.
T of highest.
Being an engineer, you have to answer this question. It's very. It's not anyway complicated. A simple circuit. Can anyone at least tell me, is it correct? I mean, is it right or wrong? If it is right, why? Or if it is wrong, even in that case, why? Mhm. And what do you think? In practice, okay, theoretically, you have already solved few problems, right? In circuit one and two. So theoretically, what do you think? Should it be zero at steady at yeah, yeah. At steady state condition? What do you think? Should it be zero? I don't get the point.
So at t equal to 0, the switch is closed. So it should be some induced voltage in the inductor. That means it should be some values of VL. But here we getting the values in 0 mathematically. So the mathematical expression is not correct.
Seriously. Any thoughts? Any other? In fact, we're talking about the steady state condition, right? We're not talking about anything about transient. Okay? So you don't need to think of a transient situation because transient analysis is something else. We're talking about, how would I say, it's more or less about steady state condition, right? Just think it this way, okay? In fact, I think I have already mentioned this one. Why don't you understand this one? At steady state condition, what's the values of this inductor impedance? Impedance values of this inductor at steady state condition? What? Yes. So when it's a steady state condition, what's the values of this? We have twice I F N. You get the point? So this frequency, is it fixed or variable? So if it is, huh? Again confused. How it is variable? Did you see the figure? Is it variable? It's a direct current.
It's fixed, sir.
It's fixed. What is the frequency of this? Huh? What's the frequency of this? A fixed current source. The frequency of this one, what? আমার তো
So
মাথায়
it's
কিছু
zero.
করতেছে না zero, right? Because it's fixed. When you say some, there is some cycle or the frequency means what? Some changes, right? I mean, when it's a fixed values, is there any change in the signal? And how could you have the frequency? The frequency is at some rate of change in the signal. So if this one is fixed, so it means f is zero. If f is zero, and we are considering steady state condition, why steady state condition? Because it is already given this I of L equal to zero or t equal to less than zero. So before you start, I mean, before you switch this one onto, I mean, on position, so then it's start at that point. And since it is a DC voltage, and if you are passing it through an inductor, what would happen? Can it form an electric field? A DC voltage, you are passing it through an inductor. Electric field.
No, sir.
So if you cannot I mean, build an electric field, how it is possible? Uh, Yeah, sorry, it's not electric. It's a magnetic field because it's an inductor. So if it cannot create a magnetic field, so how could you have a voltage across this one? So voltage across this, I mean, or if you don't want to think too much, just think of this way. This F was zero. And if F is zero at under steady state condition, so the voltage across this one, impedance zero, no matter the values of current, we don't care. So I into XM equal to zero. So this is it. So that's why you have this derivative. Okay, no matter how the value of inductance or the values of i's in the steady state condition, these values is a derivative form. This means they, because this one is fixed, so this one is zero. So under steady state condition, the value of BLT is basically zero. So if we just simply connect the, a voltage meter, yeah, voltmeter, then you see the voltage circuit. This one it's just a short circuit. If it is a capacitor, then it will become an open circuit. Okay, so when you analyze these steps, try to understand. Just not just simply just see it and just go. So you may have also little bit this kind of I mean, yeah, I can say there are some when you are giving this kind of response or waveform. So it's actually, I mean, put more effort, nothing else. But intellectually, it should be the same. Like no matter if you're just simply showing this part, this part. So here you can say there are one, two, three. At least you have to find the straight line equation for three parts, and from each of them, just okay, because you start from here and end it here in this one, and then the other part is this. Next part, we start from 4 up to 4, and then 4 to 5, 5 to 7. So you're done. And you know how to find for any questions, straight line equations, expression. Hmm? So just use the previous procedure to express the straight line equation. Just try to solve this. Huh? The solution is given here. You can also check values. So this is another example. Like you're given with this one, for example, for a signal function, you just express it with a unit step, unit step function. Note this signal function. Signal function at t equal to there is a value. At t equal to 0, this is totally 0. Okay? And for greater than and less than, there is a value. That is unity. So now you have to express this function, in terms of unit step function. Okay? In terms of unit step function. So the easiest way, as you can see, so some cases you have to use some, as I said, some brainstorming. Something you may find that it's not out of syllabus, it's within the syllabus, but things are given in different way. Okay? Everything is within the syllabus. Mm. How do you represent it? So you can take 2 ut, which means the magnitude is 2 and it's as unit step function. So you have positive and negative distance. And then what we have done is that
স্যার
this is
ক্লাস
the
টাইম
zero,
শেষ হয়ে
okay,
গেছে,
zero axis, and
আর
we
একটা
have
ক্লাস আছে।
considered. Huh? Yeah, we are almost. Yeah, we are almost done. Okay, so we have taken -1, which actually exists all over t. This means t could be any values. So what would happen then? I mean, if you just subtract this one from this one, what would happen? Twice of ut -1. So you can see 2, and here, look, this one is plus, this is -1. The twice of ut, 2 minus 1, this means 1, right? So you have this. So it's a positive system. Okay. And I think because this one is given as -1, so that should be plus. And how about this? This part, we do not have any value on this, right? So for positive ones, we have only the -1 term. So this is just -1. Okay. So you have because these values here from 0 to t less than 0 is only -1. Okay. So we have -1. So any values of t, if you can see, the values are, you can represent, for this part is +1, for this part is -1. So it's actually represent this term. Okay? And for t equal to 0, actually, in fact, the unit step function does not define any value at t equal to 0. Okay? It seems that this value is basically undefined. So at least you can represent this term, or this one. So for this and this part, you can define this, because unit step function, as I said, it starts from either t plus or t minus. It is either this or that, but not at t equal to 0. So this kind of problem you may have uh, just gives you some example, okay, what you may face. So whatever we have discussed is all about continuous in time. So similar way you can see also the discrete in time, but procedures are the same. So today's attendance, you just give it on the Tuesday, okay? And you have also exam, right, on Tuesday?
Yes, sir.
Yes, sir.
Okay, then on Tuesday, you just give your attendance. Sign it for 2 days as well, okay? So see you then Tuesday. Thank you.